I can't match you because I'm already above the line. So I'm saying that you're at 0, I'm at 1.
Okay. So here's what this looks like now. If you go to Exam 2 Content, it tells you exactly which WebWorks sets and which sections. Don't forget, there's a big chunk of the test about identifying surfaces. That's kind of an overlap from last time. So double cones, paraboloids, spheres, ellipsoids, cylinders. You have to know back and forth between equation and graph. Okay? Make sure you study. That's a big chunk of the test because we're going to use that stuff a lot in the second half. Okay, and then I gave you the cover sheet, which shows you the formulas that are given on the cover sheet of the exam. And let's see, then practice exercises from the textbook, practice problems. I'm going to add 3 more items to this tomorrow, which is the answers to odd exercises, some solutions to these. I don't think I have all of them, but some solutions to these, and then solutions to the recitation homework. So there'll be 3 more added tomorrow of these. And you have the recitation homework due tonight, the one that you worked on last Thursday. Exam Friday, and we're starting at either 11:15 or 11:45, and plan on 90 minutes. So either 11:15, 11:45. If you're in this 11:45 shift, just come in quietly as soon as you get here. Don't wait in the hallway. Just come on in, right? Don't wait in the hallway. Questions about the exam? Time to hit the books. It's hard stuff, okay? So make sure you know what's going on. Let's talk about a few. Oh, here's the saddle that I want to show you. So this actually has in 4 different directions has a minimum, and in 4 different directions has a maximum. Can you see that? So depending on which way you're coming in, so the saddle point's at the origin. Depending on which way you're coming into the origin, you're either going up and then heading back down, or coming down and heading back up. So it doesn't have to be just one direction of max and one direction of min. So that's an example of a multi-layered, I guess you call it, saddle point. Okay, so let's take a look at this one. So I'm going to talk about a little bit, directional derivative. This is actually from two WebWorks ago. So you've already handed this in. But I wanted to clarify angle measures. Angle measures related to the directional derivative. There's actually 3 different angle measures related to the directional derivative. So if we just do a generic setup here. And so we have some surface. And so this is z is a function of x and y. And so we have for any given point on the surface, how many rates of change can we talk about for a given point on the surface? So maybe this is like right here. How many rates of change are there corresponding to some point on a surface? Two rates of change?
I said
infinite number. Ronnie, what are you going to say? Infinite number. Okay, so kind of both are right. All right, so there's the 2 primary ones, and then we can, yeah, so then, yeah, it's infinite. So based on which direction you go, right? So direction then is an R2 phenomenon. So if we have like a little unit circle here. Okay, so that's a circle, right? So at our x and y coordinates in question, we can choose to go what? In any direction from that point, and then in that direction, so that's horizontal, right? Horizontal direction, that's just an R2 vector. And we said that was like the unit vector, so I'll make that say, that shows up pretty good. say like this. So going in that direction, there is some rate of change of the surface, of the z, right? So now the rate of change has to do with how much change in z per change in horizontal distance along the direction of u, right? Okay, so the first, let's extend this. Bigger circle. There we go. And then we got the red vector here. So this is the direction of the unit vector, right? So maybe that's the unit circle. So the first angle is theta. Theta is the standard trig angle that's giving us that can tell us what the direction of the unit vector is. So that's theta. And then we said there was the gradient, right? The gradient vector. We'll say the gradient vector is here. Suppose it's that way. Could be anywhere, depending on the situation. But then we said there was this angle between the unit vector and the gradient. So this is the direction of the gradient. And remember, we called that angle alpha. And why was that angle alpha important? Because the angle alpha is about the direction of max rate of change or minimum max negative rate of change or zero rate of change, right? So in order to get, so this is the direction of the gradient. Then what was the direction of max rate of change? The direction of max rate of change was, remember? The direction of the gradient. And so how do we choose u to go in the direction of max rate of change? We point it in the direction of the gradient. That makes alpha equal to 0, right? When alpha is 0, that means we're choosing u to be in the direction of the gradient, and we're choosing to go in the direction of maximum rate of change. And then if we want to choose u such that we'll have 0 rate of change, do you remember what alpha would be? 90 degree, or pi over 2 to the gradient, right? So alpha would be pi over 2, or either way, right? So there's 2 pi over 2. So that it'd be like this way, pi over 2, or this way, pi over 2, that you would choose u so that you'd be heading along a contour line, right? So it'd be like 0 rate of change. So that's the second angle. Then the third angle is what this, if you climb in that direction, at what angle above horizontal will you be climbing initially? So once we pick a direction, we calculate the rate of change. So say I'm going to pick this direction u that I've drawn there, where that u is. So then, like, here's the direction of u. Okay? And so that's the direction of u. And I'm trying to show that, like, horizontally. So maybe then so maybe the rate of change then is, so maybe the rate of change is negative. So we're kind of looking at this drawing. So in the direction of u, that would be like tangent. That would be like tangent to the surface, because this is horizontal, right? This is just moved up. So then you walk in the direction of u, and then you're going to have a rate of change based on how much z is going up or down in that horizontal direction. So maybe let's try that again. So maybe more like this. Does that look more? That looks better. Okay. So then you have the rate of change. And what's the rate of change then? The rate of change is, it would be how much change in z, like that would be your dz, per horizontal change. And the best I can do is d. This is not great, but kind of like d in the u direction, right? So like how far you go in the u direction, and then how far you go. No, that's not right. Like this. Shoot, that wasn't right. Let's try that again. So this is, the du is along this way. Du is like this. And then dz would be, this isn't a great picture. So how would that look? Yeah, I mean this is straight down like this. So this is the right angle, right? That up there is the right angle, and then this is the hypotenuse of the triangle. Does that make sense? So going along du, there's a change in z corresponding to du. That's the dz. So then there's this angle is the third angle. So this angle would be like the angle of elevation or depression for the directional derivative, right? So the directional derivative is essentially dz per d or right, so it'd be how much change up and down compared to how much horizontally along the direction of u. In this case, we have a negative rate of change. This is down, so this is horizontal, and then it's the slope is down in that direction. So so this angle here, so I'll call it beta, say. What is angle beta? Sorry, this. So what would be angle beta related to that rate of change? What's what? Nick knows. It's not on your phone, that's for sure. So how would that angle beta relate to our change in z per change horizontal? Nick, what do you think?
I would say we the arc sine of
Arc sine? What were you gonna say?
Would it be the arctangent of the slope?
Yeah, it's the arctangent. This is the directional derivative is like the slope, and so then that's kind of like that's your y or your vertical and your horizontal. So it'd be arctangent. Sorry, tangent. So the rate of change is the tangent of beta. So the angle beta is the arctangent of the rate of change. So three angles. The angle, the standard trig angle, which is the direction of u. The angle between u and the gradient when you're talking about special directions like maximum rate of change and zero rate of change. And then there's the angle between horizontal and the trajectory of your surface, which has to do with the rate of change, right? The rate of change. And that angle would be, the tangent of that angle would be the dz over how far you go in the u direction. Okay. So that's what they're talking about here. So to get this angle beta, you will need the arctangent of the directional derivative. Okay, yes, please.
So beta is like the angle between the directional derivative and the unit. I'm not really sure what
The change in z. So it's like let's make a better picture. So like if we want to go, so say we want to go in this direction, all right? So then that's a tangent to the surface in that direction. So then this is like going in the u direction here, and then you're going to have a change in z. So dz per du is your directional derivative. So that relates, that's opposite over adjacent. dz and du is opposite over adjacent, so that's the tangent of that angle. So it's the angle of, like if you're on the side of the mountain and you pick a direction to walk, it's the angle of elevation or depression that you're going to start walking on the hill. The angle above horizontal or down from horizontal. So that's highly related to the rate of change, right? The rate of change is how much vertical you make per horizontal. So that's like, in terms of a right triangle, that's like opposite over adjacent. That's what's the tangent of that angle. So this is the angle beta.
Okay, so it's between the unit vector and
Yes, the unit vector and like a tangent along the direction of the unit vector, tangent to the surface.
Okay.
So it's the inclination of the surface. Okay, so I need to practice. I need to practice making a better picture. So I don't. I hope that I didn't butcher that too bad. All right. Other questions about that? Okay, let's continue our example from last time. Which file was that? I can't remember. This one? Okay, so this one. Okay, so here we were last time. And we were making our table, right? We made our table of our critical points, and we're going to try to figure out what they were. So what were the critical points again? What were the 4 critical points? Shout them out. Let's see. 0, 2? 0, 0? Negative 1, 1? And 1, 1? Okay, and so we said to find just algebraically, so we could look, so now that we have those 4 that we found out algebraically, we could just easily compare it to the graph to figure out which one's which, right? So obviously 0, 0 is which? Local max, right? And then 0, 2, local min, and then you see there at 1, 1 and negative 1, 1 are the 2 saddle points. Okay, but so if you didn't have a graph, algebraically figuring that out means finding the discriminant. So that meant finding the second partial with respect to x, second partial with respect to y, second partial with respect to x with respect to y, and then calculating d according to that formula. Okay, and so when you do that, so we're not, let's see. There's the function there. So it's basically a matter of finding the partial with respect to x, and then find the partial with respect to x of that, and then plugging in all 4 of these, and also that you'll get these 4 numbers. Same thing in second partial with respect to y, partial of x, y. So it's just pure algebra. Partial derivatives, plugging in, right? Partial derivatives, plugging in. And then plugging into our D formula, which was fxx, fyy, minus fxy quantity squared. Okay, and when you do that, you get, for 0, 2, you get 36. And for 0, and for 0, 0, you also get 36 when you do all that work. And then for these, I think you get negative 36. And remember we said if the discriminant is negative, that's our saddle points. If the discriminant is positive, what's that? A max or a min. And then how did we decide which it would be? You go back and look at these partials. So we would expect these at 0, 2, these partials fxx and fyy to be negative or positive at 0, 2. That'd be this one. Positive, because you'd have increasing rate of change, which makes a concave up, and that gives you a minimum. So we'd expect these are going to be less than 0 based on looking at the graph. But normally it'd be the other way around. You'd see that they're less than 0, and you'd have 36, and then you conclude relative min. And then greater than 0, these should be greater than 0. At 0, 0, no, other way. Did I mess this up? Other way around. For a minimum, the rate of change is increasing, right? The rate of change is increasing. If the rate of change is increasing, the second derivative is positive. And the first derivative, or for a max, the rate of change is decreasing, right? Getting less negative or less positive or more negative. Less positive, more negative. So that gives you a max. And the max is at 0, 0. Do we have it right now? Does that make sense? That makes sense. Okay. And if you do the math, you'll get those values. You get values that are greater than 0, less than 0, you'll get 36, 36, and negative 36. So just finding partial derivatives, plugging in, and then plugging into that formula. Okay, so let's take this a step further. And I want to find the absolute max and min of f when the only points I want to look at are constrained to the region formed by x equals 0, y equals 0, and y equals 2x. Okay, so now I'm going to not let this thing go infinitely in all directions. I'm going to constrain my input, right? I constrain my independent variables to only be ordered pairs that fall within this region that has boundary x equals 0, y equals 0, y equals 2x. And with it, for all those x, y ordered pairs, I want to find what's the highest possible z value and the lowest possible z value of these. So notice that this is not the highest possible of all z values of the function, right? As soon as you move in the positive y direction, you're way higher than that. So this is what's called a local maximum, right? It's just a maximum in the local area. But then when we put constraints around it, we're saying, okay, now we want truly the highest value of z for a constrained set of ordered pairs x and y, and then the lowest value of z. Okay, so what does that look like? So what does that region look like? First quadrant. Oh, sorry. X equals 1. Sorry, not 0. So x equals 1, y equals 0. So y equals 0 is here. X equals 1. And then y equals 2x. So we're going to just look at y and x. So let's do that on our 3D graph. So how would I do that in my 3D graph? Just kidding, x equals 2. All right, so if I turn on y equals 2x, what will I get in R3? If I turn on y equals 2x, what will I get? Plane, right? Like a plane that's like a cylindrical, right? So it's going to be a cylindrical line, right? Y equals 2x extended in the z direction, like the way we think of a cylinder makes a plane. So this would be this plane. Okay, x equals 2 instead of x equals 1. And then y equals 0. So I'm going to get these planes. And so now I'm going to take that and I'm going to look right down into this thing. Here we go. Perfect. All right, just like that. Okay. So now all we care about is the xy ordered pairs that are inside that region. X equals 2, y equals 0, y equals 2x. Okay, so just like we did this, if you remember in Calc 1, you had problems like this. Where are the possible places that we could have absolute max or absolute min? Because we got an infinite number of points, we can't check them all, right? So we need to make a list of possible candidates. And then compare their z-values, and then the biggest z-value will be the absolute max, and the smallest z-value will be the absolute min. So what was that? Do you remember when we did that in Calc 1? What were the possibilities? Yeah.
Would be the critical value
Okay.
and the points at the edge.
All right, yeah, so remember, so in R2, when you had this, so you had like a interval a to b, and you had a function like this, and you had to check the critical values, like the local max and min, and then endpoints. Do you remember these problems? So the possible greatest value of, in this case, y, oh no, just happened. I lost everything I wrote. What's going on? What just happened? I did something strange here. Okay, we're back. Sorry. Clicked the wrong button in the wrong place. Okay, so you got the interval from a to b, and you got this function. And so the maximum y value and minimum y value could possibly be at the local max or min or the endpoints. So how does that transfer? How does that translate into R3? So the AB, the endpoints, translates as what in this scenario? So checking points A and B is like checking what in this scenario? What's that? What? So this is like what, the endpoints or the boundary of the interval? So what's my endpoints or boundary of this region? Yeah. Sorry. Repeating my mistake. Yeah, so this whole triangle, right? So that checking A and B is analogous to now checking all the points on this triangle, the boundary of the region. And then looking at local max and min would be the same as critical points inside, right? So critical points between A and B is like all the critical points inside. And then checking the endpoints A and B is like checking this whole boundary. So it's like we have, so each one of these pieces of the boundary is like one of these problems. See that? So yeah, so we want to check the interior for critical points. Local maxes and mins. And then we want to check the boundary. And so for the boundary, we're basically saying we got to check all the points on here. And how do we do that? So looking at, say, this, y equals 0. Well, we have to check the endpoints and all the critical points along the boundary, like a Calc 1 problem. Does that make sense? Really? So because we're going to have the overlap of these boundaries, so let's do it this way instead. We're going to check all the corners. So let's just check the corners. That takes care of, so we don't keep doing them, repeating ourselves. So we're going to check the corners of the region. And then we're going to check for local max and min on each, in between, on each boundary in between the corners. In this case, they're segments. They don't have to be segments. So we need to check the whole interior of the region inside the triangle for critical points, local max and min. And then we have to check along the boundary. And so to do the boundary, we'll check the 3 corner points, and then we'll check for local max and min along each edge. Okay? So what about, let's start with our interior critical points. What critical points do we have in the interior? So here we found those from before, right? 0, 2, 0, 0, negative 1, 1, 1, 1. We only care about those critical points that are inside of our triangle. which, if any, are inside. So this is 2, and this is the point, what, 2, 4? Is 1, 1 inside there? Yeah, it's actually right there. That was the saddle. There's a saddle right there. But since it's a saddle, can it be a local max or can it be an absolute max or min? No, because in one direction it's max, in the other direction it's min. So you've got z values lower than and greater than close by, right? So we could check it if we want. We can throw it in the mix, but knowing that it's a saddle point, we don't have to. You really only have to check the local max and local min inside the region for absolute max and absolute min. Okay, so that's a saddle point. So we could throw it in and check it, but it's not going to be our absolute max or absolute min. So now we've known that. Boom, check. And so say we had a local max. Say we had a local max in there. How would we check its z value? How would we get its z value there? Yeah, plug it into the function, right? So you're just going to take the ordered pair for your critical points and find the z value, which is the value of the function. And that's going to be true for all our candidates, right? So all these candidates that we come up with for potential absolute max or potential absolute min, we're going to apply, we're going to just evaluate them in the function. And we'll get a z value, and then we're going to compare the z's. So there's really, in this example, there's the saddle point, but don't have to do it. Don't have to do it. All right, so now we're to the boundary. So let's start with the corners. So the corners are 0, 0. 2, 0, and 2, 4. So these are potential candidates for absolute max and absolute min. So we'll just get all our candidates, and then we'll evaluate them in the function to get the z's later. So we got the corners. Last thing is local max and min along the edges, all right, along the edges. Okay, so this was 2A. So now 2B. Edges. So how am I going to get? So we'll start with this edge here was y equals 0. So I'm going to do a mini, like I need to find local max and local min along that edge. Right? So along that edge. So how do I do that? If I'm talking about this gold function, I know that y equals 0, then I can do what to the function? Plug in y equals 0. So I can do fx comma 0 and get a function of x. So it's going to be 0, 0, minus 3x squared, I think it is. Everything else cancels out. Is that right? Because y is 0. Okay. And so then I'm going to take f prime of this function of x. I'm going to get minus 6x. And I'm going to set that equal to 0. I want to take the derivative of this single variable function, set equal to 0 to find critical points just along that edge. And I get x equals 0, which is, I already have that. That's one of my corner points. Don't have to check it again. So done with the lower edge. Making sense what we're doing here. Next edge, x equals 2. Okay, so I'm going to take now x equals 2y, and we're going to have a single variable function in terms of y. So now this is a little more involved here. So we got 2, 4, is that 12y? Check my math. 12y plus y cubed minus 12 minus 3y squared. How did I do? And now I take the derivative of that. Because I'm checking for local max and min along this. So I want f prime with respect to y. And I'm going to get 12 plus 3y squared minus 6y. And I want that to be 0. Everything look good? So I think I have a factor of 3 here. I can since I'm equal to 0, I can divide by 3. So y squared minus 2y plus 4. And I think that does not have any real solutions, right? So we might try to factor this or use the quadratic formula, but I think b squared minus 4ac is a negative number. So no real solutions. Questions? Are you guys settled? Good?
There's a plus to the original equation, which kind of
Say it again?
there's a plus to like the original equation, which kind of I don't know if it makes sense.
Let's see. So, so it makes a difference for this. This would be, so minus 12 plus 2. But then when we get to the derivative, it doesn't. So no, but I'm glad you pointed that out. So this function should have been 12y plus y cubed minus 12 minus 3 squared plus 2. That should have had a plus 2. But it ends up being inconsequential because it goes away when we get to the derivative. What about this? We blow this one too? So yeah, so it should have been 3x minus 3x squared plus 2. For the function, again, though, derivative is just minus 6x. Is that cleared up? Okay, thank you. So y equals 0 didn't yield anything. X equals 2 didn't yield anything. So finally, what do we have? Last one is? So this is the interesting one. So y equals 2x. And so again, I want to create a single variable function out of my surface function along y equals 2x. So what will that be like? How will so I want to get a single variable function for the part of this gold function that lies along y equals 2x. What will I do? So f of x 2x. Okay, so I'm going to leave this to you now. So you're going to determine what the function is, and then determine if there's any critical points along that
Property. Basically, if you have a times b equals 0, either a has to be 0.
5/7. Did you get 5/7?
Yeah.
Okay, so what do we have? Do we have is there a local max or a local min at 5/7? So somewhere along here, there's something happening. 5/7 is, this was 1, so 5/7, 10/7. So there's this point right here. How do we determine what's happening at 5/7? What's that? Second derivative, right. Second derivative can tell us. What's the second derivative? 14, is that showing up? Yeah, 14x minus 5. Plug in that value, 5/7. And we ask, is it positive or negative? So 14 over 2, is that equal to 5?
Yeah.
So at 5, so this is greater than 0 at 5/7. What does that mean about that? If the second derivative is greater than 0, that means what? The rate of change is increasing. Local minimum along that edge. There's some local minimum along that edge at 5/7, 10/7. So that becomes part of our list then. So we're going to have the point 5/7, 10/7, which will be part of our list of candidates for absolute max and absolute min. So how many total candidates did we get? I think just 4, right? We just got we could include the saddle point 1, 1 in there, but we argued that that doesn't belong. So candidates, corners, saddle point, but we know that won't be one of them. And then our local min along the edge y equals 2x. And so now how do we find the max z and the min z? Just plug them in. So I think I've already done that. So I've defined the function f here. So there's f0, 0. That's just what you get when you plug in 0, 0 is 2. There's the 5 sevenths, 10 sevenths. We get negative 0.55, 1, 1. We know that couldn't have been right because that's the saddle point, but there it is. 2, 0, and 2, 4. So there's our list of z's. 2, negative 0.55, 0, negative 10, 54. Absolute max is? So the absolute max is 54. And let's stand out here. So right there, z equals 54, and that's our absolute max at 2, 4. Absolute min? The lowest of those z values. So it looks like at 2, 0, negative 10. Here. Okay, questions on this process or what's going on here? The idea. And so maybe we can, well, I don't know, leave that up so we'll get it down. Last chance. Okay, yeah, you good? All right, so like I said, recitation tomorrow. You're gonna just be working hard studying for the test. You got your written homework due tonight. Okay, so let me clarify what's on the exam for this stuff. So stuff that we covered Monday about the second derivative is fair game. But optimization, like this kind of thing, optimization is not on the exam. But stuff about the second derivative could be. Okay? And then the optimization web work will push till like Monday. Okay? So you don't have to do it Friday. Okay?